Alright gang, so this is going to wrap up the physiology of muscular system. It's kind of a second step after you feel pretty good about the steps of the muscle contraction. But we are going to start off, or I'm going to start off, by reviewing those steps real quickly with you. Okay, so remember that this structure that is right up here, this is a myofibril. That is one little piece of a muscle fiber, right? And around each myofibril, if you zoomed in, around each myofibril, you have that sarcoplasmic reticulum. Okay, it's that little blue bag around the outside there, and that's filled with calcium, right? So that's important to remember. And that inside each myofibril, that's where you have the actin and myosin. So if you look at those from the side, remember you've got smack dab in the middle here, this is the actin. There's one piece of actin. There's another piece of actin. And reaching out towards it, you have myosin on each side, reaching out towards it. And that the myosin heads, these little pieces sticking off, or cross bridges, are trying to grab hold of these active sites, these binding sites that are shown in gold here. Okay. Now, because the gold sites are blocked by the troponin and tropomyosin, that's the this brown and blue section in there, they cannot bind, okay, until we release the calcium. So remember, the electrical impulse comes down from the brain. It's going to stimulate the, it's going to cause release the acetylcholine. That acetylcholine is going to go across and bind. It causes an impulse over the surface, goes over the surface in through the T-tubes, and causes these sarcoplasmic reticulum channels to release all this calcium. So the calcium comes out, and remember, it binds to the troponin and tropomyosin, causing them to change shape and move out of the way. The binding sites are now exposed, so we get binding. Voila. And they grab hold. And as long as there's ATP, those heads will start to bend, and they'll start causing a muscle contraction. From the end result is that the myosin, shown here in purple, pulls the actin inward. And you can imagine this whole section, notice the length here, so that the piece called the H band in the middle shrinks. So these two pieces go in on either side, kind of like you're collapsing an accordion. All right? Just looking at the exact same thing from the side view, binding blocked, calcium comes in, unblocked, and now we'll get binding. Okay? But what I want to focus on here is this chunk at the beginning. So notice ADP plus P. That means that used to be an ATP. Okay, so ATP is already bound to these heads, okay, and charged them and had those myosin heads or cross bridges ready to go. So the ATP is needed for this phase of it. Okay, you also need ATP when you get the release. So here comes the head bending. Right, so that's showing the head bending, it attached in this one, it bends in this one, and we're shoving the stuff along. But then notice this, ATP is also needed to get the heads to let go. Okay, so ATP is needed not only to move the heads, to bend them, to cause the contraction, but it also is needed to kind of reset them so they can do the whole thing again, or at least let go. All right, so a couple thoughts. All right. First one up here is called the threshold stimulus, okay, threshold stimulus. So each muscle fiber has a certain amount of ACH needed for it to contract, okay. Now, in a muscle, they don't all have the same threshold stimulus. So let's say we've got 10 muscle fibers inside a certain muscle. So here's your muscle, and inside here you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 muscle fibers. I don't know what happened to that last one. Let's get rid of him. Bam. Okay. I need one more, don't I? There you go. All right, you got 10 muscle fibers. Each one of those muscle fibers needs a certain amount of acetylcholine to contract. All right. So some are going to have a really low threshold. That means one acetylcholine will make them contract. Okay. So when a motor neuron comes down, connects in here. All those muscle fibers are going to get one acetylcholine. And only one of these guys, let's say that guy right there is the one, he contracts, and you get a really weak contraction. Maybe you're picking up a piece of paper, or you're just bending your arm to scratch your face, okay? Let's say you needed to move something a little bit heavier, alright? Now you might send 4 acetylcholine down. So here comes 4 acetylcholine down this motor neuron now, a little faster frequency, more acetylcholine release, and now, not only does this one reach its threshold, but this one reaches its threshold, this one reaches the threshold, this one. So now you might say have 4 of those muscle fibers helping, and that makes a stronger contraction. These guys over here in purple, they're just watching. They're not really helping in the muscle contraction. Okay? So if we need even stronger, let's say you're now trying to pick up, you're trying to pick up your your desk, all right, and you need a stronger contraction than that, you might say send 7 acetylcholine, and that will now reach the threshold for all of these guys still, but now it'll add a couple more guys. Now these guys help. So every time you add more acetylcholine, you just recruit more people to help with the contraction, more muscle fibers to help with the contraction. A maximal contraction, remember, we can send about 1,000 action potentials per second down here. So if we really send 1,000 action potentials per second, we would be able to stimulate every muscle fiber in here, and your muscle would contract as strong as it possibly can. Okay? So the keys here is to remember that each muscle fiber has its own, each cell has its own minimal amount, and it's not the same for every muscle fiber in your body. So for your bicep, some muscle fibers will contract with a little bit of signal from the brain, but some of them won't contract unless you send everything from the brain, and that's how you control the amount of strength you need. All right. The second one is the second part of this is really important as well. It's the all or none. So if it reaches its threshold, it contracts as hard as it can. So if we were to get rid of some of this, let's clear all the ink off. Okay. So if this is our muscle fiber again over here, right? And this guy right here only needs 1 acetylcholine. Okay, that muscle fiber only needs 1 acetylcholine. It contracts just as hard if you give it 1 acetylcholine as if you give it 1,000. Okay, once it reaches threshold, it contracts as hard as it can. Okay, and then if this one also reaches threshold, it helps as hard as it can. There's nobody like halfway pulling. So imagine like tug of war. Okay, if you've got one person pulling on the rope, they have a certain amount of strength, but they're pulling as hard as they can. Another person just got recruited. This guy came in and helped. The 2 of them are pulling as hard as they can. A third one gets recruited because there's enough acetylcholine. They're pulling as hard as they can. But these guys don't, pull stronger just because there's an extra person there. They're still pulling as hard as they can. All right? And that's what the all or none idea is. If it reaches threshold, it's pulling as hard as it can. All right, so as we just talked about a moment ago, is the fact that we use a lot of ATP, a lot of energy for muscle contraction, okay? And typically, you only have enough ATP in your muscles for about 2 or 3 seconds of contraction, okay? So if you you leave my classroom and you start jogging to the Submasters or across the building, okay? By the time you are halfway down the hallway, you've already used up all the ATP in your muscles. So we have to make more. That's the key. And we do this. We need energy right here to take ADP, diphosphate, plus another phosphate, and make more ATP so we can keep contracting. All right? So the first thing that we use is what's called creatine phosphate. A lot of you guys have heard about creatine phosphate, and it is a really cheap energy source. It's found in every muscle. You get some of it from any time you eat meat. Many of you also have heard of creatine phosphate because that's a supplement that a lot of people take for like weightlifting and so forth. And typically, if somebody takes this for weightlifting, what they can do is they can increase this 2 or 3 seconds of cheap energy to maybe all the way up to 3 to 4 seconds. All right. So for all the money and theoretically puts a lot of wear and tear on the kidneys to add all this in because you pee out most of the extra creatine that somebody takes the supplement. All you get is really about 1 more second of energy before you get tired, which if you were a sprinter, world-class sprinter, 1 more second before you start to feel fatigue in your legs probably might be worthwhile, but for the typical person playing a basketball game or a football game, not worthwhile at all. So it's a waste of money. Right? After that, after the creatine, we then just use cell respiration. Okay, and to start off with cell respiration, we'll use aerobic cell respiration when we have plenty of oxygen, and that makes a ton of ATP for us. But as you know, we can't keep up with that supply. So ultimately, we will start having to turn to anaerobic cell respiration. Okay. So where does the oxygen come from? Well, hemoglobin carries oxygen. Okay. In your blood, that's what's in red blood cells, carries the oxygen, and myoglobin is what makes your muscles red. It's just like hemoglobin. It's pretty much the exact same structure. Notice the names. Okay. Myo is that prefix that means muscle again, right? So it's muscle globin. And it stores extra oxygen in your muscles so that you actually have it ready for this process, so that oxygen can be released for cell respiration. Okay? As soon as we don't have enough oxygen available, we then switch to anaerobic cell respiration, which is also referred to as glycolysis. And glycolysis is not nearly sufficient. It produces very little ATP, someplace in the ballpark about 2 to 4 ATP per molecule of glucose versus 36 that we got up here when we had oxygen. So it doesn't make much ATP, and it also makes lactic acid as a byproduct. And you're going to see in just a moment that's what makes us tired. Okay? So this is our process, guys. This is how we fuel our muscle contractions. So following an exercise, we often have something that's referred to as oxygen debt. So oxygen debt is the amount of oxygen that you need to put yourself back in normal. So you've all noticed it at some point. If you've been running or playing, practicing, or doing something, and you stop, you're still breathing heavy. You don't immediately stop breathing heavy. That's because your body is trying to return to its normal homeostasis state. So it's got to do all of these things. We need oxygen to get rid of the lactic acid you've built up in the body. We need oxygen for cell respiration so we can replace the ATP and the creatine that are normally stored in the muscles ready to go. All right? And then we also need oxygen to kind of refill that myoglobin. Remember, that's what stores extra oxygen in the muscle. Okay? So if I go and play basketball, my breathing will actually be noticeably. I'll be breathing heavy for minutes after I stop playing, but it's actually hours later. You'll still be breathing. If you actually practice hard at something, you'll still be breathing 2 or 3 or 4 breaths more a minute, trying to replace all this oxygen, replace all these things to make up for what's called the oxygen debt. All right, so one of the big ideas that comes up every year is this idea of muscle fatigue. That's just muscles getting tired, right? And what happens in muscle fatigue is you actually get lactic acid starting to build up in the muscles. So lactic acid, remember, comes from the anaerobic cell respiration. You didn't have enough oxygen to keep up with the muscle contraction. So the lactic acid starts to build up in the muscle, and that changes the pH because it is an acid. It's a weak acid, but it's an acid. So it's going to drop the pH, right? Remember, acids are low end of the pH scale. And what happens, that means the muscle fiber is less responsive to the ACH. So a muscle fiber that needed, say, only, needed 70 acetylcholine to contract before, because of this change in pH, okay, because of the change in pH, it now might need 10 acetylcholine, okay? So it makes it harder to make the muscle fiber contract. Right? The ones that we really care about when you actually start to see the muscles getting tired is you have some muscle fibers that their starting number might be 100 acetylcholine. Let's say that's the very most you can release on a muscle fiber. So this is, you need like 1,000 action potentials per second to make this happen. All right. Well, if with pH, if that number changes and all of a sudden you need 110 acetylcholine, we can't do that. We can't produce enough acetylcholine in that period of time, so this muscle fiber no longer contracts. So your muscle just got weaker. And the more you exercise, you'll drop out more of them. So the ones that needed 90 acetylcholine will not be able to reach threshold anymore. The ones that needed 80 won't be able to reach threshold, and the muscle will continue to get tired and tired and tired. And that's why you can't sprint indefinitely. If you keep running at a sprinter's pace, your muscles will eventually collapse. They'll essentially turn to jelly because the muscle fibers will no longer be able to contract. All right, and that's the big idea with muscle fatigue. All right, tying this into muscle fatigue, there's actually lots of different muscle types. We're going to break it down into the most simple way, guys. We're going to call them type 1 and type 2. Okay, so type 1 are called slow twitch, and they're red muscle. Okay, and what happens is they are actually really good at endurance. Their muscle fibers are really good at endurance. So they have lots of mitochondria for cell respiration. They have more myoglobins. They have more oxygen in there. So the better they are at aerobic cell respiration, the less lactic acid, so the muscles don't get tired. So if you are packed, if your muscles genetically, if you were born we're all born with a ratio, if you were born with, like, say, 80% of the type 1 fibers, you would be a very good endurance sport athlete, a marathon runner, a distance swimmer, things like that, because you're going to have muscles that don't get tired very well. You'd have a very good chance, especially if you train them to make them even better, you'd have a very good chance of those sports. Okay? Type 2 are called fast twitch, and these are the ones that give us the explosive stuff like jumping and sprinting and so forth. They're white because they don't have a lot of myoglobin in them. They're glycolytic because they don't have a lot of mitochondria for cell respiration, so they get really tired really quickly. So you'll notice this. I always get frustrated when I watch the NBA, and I think most of the NBA players, you look at them and like, boy, that guy's lazy. He's just standing there watching, not doing anything. Well, most of the NBA players are loaded with type 2, okay? So they might be, say, 80% with type 2. And that means they can jump really well, they can sprint really well, they're explosive. That's what these muscle fibers do. They give people their explosive, quick movement, but they're crappy at endurance, so they're going to get tired much more quickly. Now, regardless of what your natural makeup is, if you were, say, 80% explosive, if you work really hard, you can make this other 20% better, and you can get better at your endurance. Or vice versa, if somebody was mostly these endurance muscle fibers, they could make this other 20% better, and they could actually get become a better sprinter and so forth. But if you were born with lots of type 2, you're never going to be a successful marathon runner. Okay, you can get better at it, but you're never going to be great. And if you were born with lots of these type 1, you got great endurance, but you're not going to be a high jumper or a sprinter. It's just not going to happen. Okay, those guys that seem to be really good all-around athletes, they're typically pretty well mixed. They have a nice blend of both of these, so if they train both the muscle fibers and they work hard at it, they can actually succeed in both settings. And here's a little diagram to give you an idea, okay? So your eye, think about how fast your eye twitches, guys. That is going to be a lot of that type 2 fiber. The muscle contracts really quickly and bounces right back into place. Your gastrocnemius, okay, is really good for jumping, versus the soleus. Remember, the soleus is underneath. That's going to be a lot more of that type 1, the slow twitch. So fast twitch for the gastroc, which allow you to really jump and sprint, and the soleus is going to be much better typically at endurance events. And in this picture, they're just trying to show you the difference in color. So here you can notice this is not very dark, okay, so this is very kind of light. And because it's lighter, it doesn't have as much of the myoglobin, doesn't have much of the mitochondria, and therefore it's not very good at cell respiration, and it gets fatigued really easily. Versus over here, it's much darker, it's got more myoglobin, got more mitochondria, and it's fatigue resistant, so it's pretty good at endurance sports. Alright, so the last little piece that I want to show you guys is just kind of something that I just find really interesting when you look at it. Okay, so what this is showing you is the length of the muscle. Okay, so this is the length of the muscle. Okay, and over here is how much tension it can generate, how much force it can generate. So let me get rid of that because that's getting in the way. So this is tension, how much tension it can generate when the muscle contracts. All right. So you'll notice, first thing you might notice is that when your muscle is kind of medium stretched, kind of right in the middle, we're really strong. Okay, so for instance, if you had your bicep, instead of your arm being completely straight, if your arm's kind of bent right in the middle, you're pretty strong. Okay, but if you stretch your arm way out, you become really weak, or if you actually contract it all the way, the muscle actually becomes a little bit weaker. And they've got two different reasons for it. If you look over here, if your muscle is completely stretched, so if you've got your arm hanging straight all the way, your elbow is fully extended, so everybody kind of fully extend that. Okay, your bicep does not have much overlap. Look how little overlap there is between that actin and myosin. Okay, so very few. Remember, the myosin is the purple, the actin is the red. There's very few of those myosin heads that are actually able to attach to the actin and generate force. Okay, as you move inward a little bit, and you bend your elbow a little bit and raise your hand a little bit, you get more pieces attaching, more cross bridges can attach, so you can actually generate much more force pulling those pieces inward. And here we have maximum area for attachment. So now this is as strong as the muscle can be because you have lots and lots and lots of cross bridges attaching. On the other end, when you start to bend the muscle all the way, so if you bend your elbow the whole way, and it's almost like you're touching your shoulder with your own hand, right? You're going to start seeing those actin pieces start to actually jam together in the middle. Look at this. They're actually overlapped in this section here. Okay? And when they become overlapped, they actually start to collide and actually repel off each other almost like a spring. So they kind of bounce back in the opposite direction. Okay? So when is this important? Well, if you actually watch in the gym, you'll actually be able to see. If you go to the gym and you watch somebody, you'll be able to see if somebody's using too much weight. If somebody is using the proper weight, they will be able to fully extend the muscle So if somebody's doing like bicep curls, they'll be able to fully extend their arm, and they'd still be able to lift it up. But when somebody's using too much weight, because the muscle's weak here, they'll only bring their arm down part way. So imagine this is the humerus, okay, and here's the radius and ulna, and here's my hand holding a dumbbell, right? So I should be able to straighten my arm all the way and yank that weight up in this direction, right? But if I'm using too much weight, I won't do that. If I'm using too much weight, I'll do this instead. I'll have my arm here, and I'll only go down this far. Because if I extend any further, my muscle gets too weak and the weight will get stuck down there. So you'll see the person that only goes down part way. Or with like bench press, they'll only go part way. They won't bring the weight all the way down to their chest or whatever it is. So this is a pretty good indicator where when I'm watching somebody, I can get an idea of whether they're using too much weight or not. If you can't fully extend on an exercise, you can't bring the weight all the way to your chest, you can't pull all the way out, then you're actually not working the full length of the muscle, and you're actually not getting as much out of it. So this is typically a very bad sign when somebody can't extend their arm all the way and continue doing the exercise. Right? So hopefully this helps, guys. It's a lot of stuff in here, and I apologize for how much in there, but we got to find a way to get this out. So come see me if you have any questions. We're going to go over a lot of this in one of the case studies in class as well. But if you have this as the background research, and hopefully you jotted down some notes on that packet, it'll make your life a whole lot better. All right? Take care.